All right, welcome. Today, we're going to pull back the curtain on the absolutely masterful cellular heist carried out by Shigella, the bacteria behind dysentery. In this first part, we're going to cover the initial break-in, how it gets past the body's toughest defenses. And then, in our next explainer, we'll get into how it spreads and unleashes its most dangerous weapons. Okay, so let's just start with a number that tells you almost everything you need to know about how serious this pathogen is. And that number is 10. That's it. It can take as few as 10 of these tiny little organisms to cause a full-blown infection.
And to really wrap your head around how wild that is, let's put it in perspective. Look at something like Vibrio cholerae, which causes cholera. You need millions, sometimes hundreds of millions of those bacteria to get sick. Shigella can do it with just a handful. It's built for pure efficiency.
So how on earth does it manage to be so effective? Well, its first trick is surviving the acid death trap that is our stomach. While most bacteria are just dissolved, Shigella fires up these really clever molecular systems that basically just consume the acidifying protons around it. It neutralizes its own little patch of stomach acid and just sails right on through, totally unharmed.
So it's made it through the stomach. Challenge 1 is down. But now it faces its real target, and its next big problem, the colon. You have to think of the colon wall as this tightly sealed fortress, designed specifically to keep all the bacteria inside the gut from ever getting into our body.
Now, a frontal assault on this fortress would be a waste of time. Instead, Shigella is way smarter. It looks for a built-in vulnerability, a weak point, and it finds one in our M cells. You know, these cells are supposed to be our own lookouts, our surveillance system. Shigella sees them as an unlocked backdoor. And here's how the infiltration goes down. It's this slick, three-step process. First, Shigella lets itself get picked up by an M cell. The M cell, just doing its job, then carries the bacterium across the entire fortress wall, a process called transcytosis, and then it just releases it on the other side. Just like that, Shigella is inside, completely past our main defenses.
Okay, so it's in. But it's not home free yet. The second it gets deposited into that deeper tissue, it runs smack into a resident macrophage. And this guy is the first responder, the beat cop of the immune system, whose whole job is to find invaders and destroy them.
Now, for almost any other bacterium, getting eaten by a macrophage is game over. It's a death sentence. But for Shigella, this is all part of the plan. Getting engulfed by the very cell designed to kill it, well, that's not the end. That's the trigger for the main event.
See, Shigella doesn't just try to escape. It turns the macrophage into a suicide bomb. It triggers this incredibly violent form of cell death called pyroptosis. And this isn't some quiet, orderly cell death. No, this is a detonation. It's designed to cause maximum chaos and to scream out inflammatory alarm signals to the rest of the body.
So how does it light the fuse? It's amazing. Once inside the macrophage, Shigella deploys this tiny molecular syringe and injects a protein, IcsA, right into the cell's interior. This protein is like a specific key that finds and turns on an enzyme called caspase-1. And caspase-1, well, that's the master switch for pyroptosis. The moment it gets activated, the fuse is lit, and the macrophage just violently explodes.
And right there, that's really the clinical pearl for this whole section. Shigella doesn't just run from the immune system. It hijacks it from the very first moment. It's a key idea to hold on to. And hey, while we're pausing, if you're getting something out of this, please go ahead and like and subscribe. It really helps us make more of these for you. All right, now let's talk about the consequences of this explosion. So this brings up the obvious question, right? Why? Why do all this? Why evolve this insane strategy of blowing up your first hiding spot? What is the advantage for Shigella in creating all of this inflammatory chaos? Well, the answer is just diabolically clever. For one, the explosion sets the bacteria free. But that's not even the main point. The exploding macrophage releases a flood of chemical alarm signals, cytokines, like IL-1 beta and IL-18. These act like a massive flare screaming for backup. And that backup comes in the form of a huge swarm of neutrophils, the foot soldiers of our immune system. As thousands of these neutrophils come rushing to the scene, they are so frantic that they literally tear open the junctions between the colon cells, ripping huge holes in that fortress wall that Shigella had to sneak through before. So you see, this is the crucial takeaway. The chaos, the inflammation, the damage, it's not collateral damage. It is the plan.
Shigella masterfully weaponizes our own immune response against us to blow the gates of the fortress wide open. This creates the absolute perfect conditions for its real invasion to begin. And that's exactly what we're going to dive into in part 2.
Oh, there are so many yummy vegetarian options out there. You could try like lentil soup, veggie burgers, tofu stir-fry. The possibilities are endless. All right, welcome back. Now continuing with IcsA, actin comet tails, and Shiga toxin, we're going to dive into the two really devastating virulence mechanisms that Shigella uses after it's already inside a host cell. We're going to look at how it moves and, well, how it kills. So let's get right into it. Once Shigella is inside one of your colon cells, it has a huge problem. This bacterium has no flagella, which means it's non-modal. It can't swim. So how in the world does it get around? Well, instead of swimming, it pulls off this brilliant act of intracellular guerrilla warfare, hijacking the cell's own skeleton to build itself a motor.
And the ignition switch for this whole thing is a protein called IcsA, which you might also see called VIRG. Now, what's truly amazing here is its placement. Shigella only expresses IcsA on one end, one pole of the bacterium. And this is absolutely critical. Why? Because it makes sure all the force is pushed in one direction, turning the bacterium into like a guided missile instead of just a spinning top.
Okay, so how does this motor actually get built? It's this beautiful and frankly ruthless molecular cascade. First, that apicoxA protein acts like a grappling hook. It reaches out and recruits a host protein called NWASP. Once NWASP is hooked, it flips a switch on another host complex, ARP2/3. And this is the key moment. ARP2/3 is the master builder for actin in the cell. When it's activated, it just kicks off this explosive growth of the cell's own actin filaments right at the back of the bacterium.
So, all this incredible molecular machinery, what does it actually create? Well, the answer is a super efficient system for propulsion and, even more importantly, for invading the cell next door. And the result is what you're seeing here, an actin comet tail. I want you to picture a rocket. The continuous, super fast assembly of actin filaments at the back of Shigella is basically the exhaust. The sheer force from this polymerization gives it this powerful, sustained push, propelling the bacterium right through the thick, soupy cytoplasm like a microscopic torpedo.
Now, here's where the strategy gets really genius. The bacterium doesn't just joyride around the cell. No, it drives directly into the cell membrane of the colonocyte right next door. The force is so great that it actually pushes out this finger-like protrusion, still wrapped in the first cell's membrane, right into its neighbor. The neighboring cell then just engulfs this little package. And once inside, Shigella simply breaks out of the double membrane, and it's free again, ready to start the whole process over.
By spreading this way, the bacteria never have to go out into the extracellular space. This means they're effectively hiding from antibodies and all the other immune defenses lurking out there. It's a truly clever strategy. We're about to switch gears to Shigella's second weapon, but hey, if you're finding this breakdown of microbial tactics useful, please like and subscribe for more custom medical videos made just for you. Now, moving on to the next segment.
Okay, so we've covered Shigella's physical warfare. Now let's turn to its biochemical attack. You see, while other Shigella species are focused on invasion, Shigella dysentery type 1 comes armed with an extra weapon of mass destruction, the Shiga toxin. And this isn't some blunt instrument. It's a weapon of precise molecular sabotage.
Shiga toxin, or STAX, is what we call an AB5 toxin. It just means it has one active A subunit and 5 binding B subunits. But the real key classification here is ribosome inactivating protein, or RIP. And honestly, that name tells you everything you need to know about what it does. It's designed to find and destroy the cell's protein factories, the ribosomes.
Let's walk through this little sabotage mission. First, the B subunits find and bind to a specific receptor called GB3, and that gets the whole toxin inside the cell. Once it's in, the active A subunit is released. It acts as an N-glycosidase, which is basically a type of molecular scissor designed to cut a very specific bond. Its target, a single adenine base within the 28S ribosomal RNA. With surgical precision, it snips out that one adenine, and that one single cut, it is catastrophic, and it's irreversible. The ribosome is permanently dead. Protein synthesis grinds to a total halt, and the cell is basically sentenced to death. So we have this incredibly precise molecular event, right? One single base cut from one RNA molecule.
The final piece of our puzzle is to understand how this microscopic act of sabotage translates directly into the macroscopic clinical signs of bloody dysentery that we would actually see in a patient. So the question we really have to answer is this. How does a single molecular cut lead to bloody dysentery? How does one broken ribosome become a hemorrhagic colon?
Well, the answer lies in this devastating cascade of events. The widespread death of colon cells and the endothelial cells lining the gut's tiny blood vessels leads to microvascular injury. The little capillaries get damaged, they get clotted off. This chokes off blood flow to the mucosal lining. That's a condition called ischemia. And that causes tissue death and massive bleeding. The result is hemorrhagic colitis, which produces that classic dysenteric stool filled with blood, mucus, and inflammatory cells. So let's just end with this thought. Shigella has this sophisticated two-pronged strategy: physical hijacking to spread stealthily between cells, and biochemical sabotage to destroy the tissue from the inside out. What does this incredible dual approach, this combination of, brute force and molecular precision, really reveal about the intricate, ongoing evolutionary arms race between pathogens and their hosts?